Hello, everyone, and welcome to the first episode of Common Factors. So, not only is this the first episode of the Combinatorics series, this is also the first episode that I'm recording. Now, Common Factors is dedicated to taking mathematical concepts which you might have an intuition for and turning them into rigorously defined formal concepts that we can actually use in formal mathematical proofs. And one of the areas that I found tricky to formalize when I was studying it is combinatorics. I studied this at A level, and we never went deep into the formalization of all of the combinatorial mechanics. So I thought we would start the channel off with the series on combinatorics. As such, we will begin with some basic rules about the sum and the product. There is some assumed knowledge for this particular course. In particular, we assume familiarity with sets. So we assume that you're familiar with what a set is naively as a collection of elements. We assume you're familiar with the notation for sets, both the listing notation and the set builder notation. We also assume familiarity with the Cartesian product. That is the set of tuples of length k, where all of the elements of that tuple come from a particular set or a particular collection of sets. And I believe that's all knowledge that you'll need for this course. So, without further ado, let's begin. Before we start, I want to ask the question of what combinatorics actually is. Fundamentally, it is the branch of mathematics which is fundamentally concerned with counting and enumeration. So it is involved with things like counting sets, or the sizes of sets, the cardinalities of sets. It's generally associated with discrete maths because it's useful in things like graph theory. But for this course, we'll be considering it as something fundamental, and we're not going to be concerned about its applications in areas like probability theory and graph theory. So we'll only be concerned with enumeration for enumeration's sake. Now, combinatorics is fundamentally related to sets, and so we're going to be using a lot of set notation. And the first thing that we're going to consider is if I have a set A with n elements and a set B with m elements, and A and B are disjoint, or how many elements are in the union of those two sets. Now that's not too hard to figure out. Since the sets are pairwise disjoint, we're not concerned with any double counting. So the answer should be n plus n. But here's a question. Can we apply that to thinking about choices? And to do that, I'd like to offer an example. Suppose we have two political parties with leadership candidates for a general election. Now, obviously, I'm not going to name these political parties, so we will just call the set of leadership candidates. We'll say that the political party A has leadership candidates A1, A2, and A3, and the political party B has leadership candidates B1 and B2. The question we want to ask: how many choices are there for the winner of the general election? Now, there are a few important things that we have to note about this. You might think the answer is obvious. There's obviously 5. There's 3 candidates from A and there's 2 from B. 3 plus 2 is 5. That's true. That is the answer. But there's something very important that we have to note. A and B are disjoint. That is, A intersect B is the empty set. What that means is that none of the stuff in B, that is, none of the candidates of political party B, are also running as political candidates for party A. And that's really important, because if we think, what if we had A defined as A1 and A2? So you have your 2 candidates there. But what if they, or at least one of them, like A1, was also running as a candidate in party B? Obviously, that would never be allowed to happen. But if it were, you would only have A1, A2, and B1 as choices. That's 3 people, even though 2 plus 2 is 4. This is the kind of nuance that we need when we formally state a theorem like this. Now, I'm not going to prove this because it's very elementary, but here is the theorem. The sum rule. If there are n ways to choose things out of a set A, and m ways to choose things out of a set B, and A and B are disjoint, there are n plus m ways to choose things out of A and then out of B. That's the combinatorial rule of sum. So the rule of sum is one of those theorems which is fairly intuitive and it makes sense. And in fact, the proof of the sum rule is incredibly simple. It simply involves listing the elements of the first set and the elements of the second set and just counting them. And it's nice and simple. Now, we're going to move to a rule which is fairly easy to see intuitively, but the proof is a little bit more complicated. We're going to have to talk about partitions, and that's slightly tricky. But we're going to do it. No worries at all. So, let's do a little definition here of partition. We're going to let A be a set, then the family of sets, so the family of sets given by the following, and we're going to assume that it's finite, so you have k of these, is a partition if, and then we need the following to hold. No A sub I is empty, so all of the sets have something inside of them. And then every element of A is in exactly one of these A sub i's. And finally, though this follows from the second point, the union of these sets, so I'll do I equals 1 to k of A sub I, is equal to our original set. So just to draw a little diagram, suppose this is our set A. A partition just splits the set up into some pieces so that the pieces don't overlap. None of the pieces are empty, and all of the pieces together form the whole set. That's all a partition is. Nice and simple. Now what you might have noticed is in the sum rule we had that if A and B are disjoint and they cover all of the possible ways of doing things, then you get out the sum rule. And this is the generalization of the sum rule. So I'll write out the sum rule in its most general form. We'll say let A be a set and we will assume a finite partition of A. Then the size of A is simply the sum of the sizes of each of those sections of the partition. And hopefully that seems fairly intuitive. Remember, we're not proving this, and we will not prove the general version of the multiplication rule either, since things become a lot more complicated. But those proofs follow from the proofs for only two sets. And that brings me on nicely to the multiplication rule, which I would call the most important rule in combinatorics. It is used everywhere and we will use it a lot in the future. So, the theorem states if there are n ways to make a first choice and m ways to make a second choice, there are n times m ways to make the first and second choices together. Now, it's worth understanding why this is different from the sum rule and why we have a different expression. In the sum rule, we had two sets which are disjoint. Each of those things was counted essentially as a first choice, right? We weren't thinking about making a first choice and then making a second choice. Here, we're thinking about making a first choice from these n elements and then making a second choice from the m elements that we have. So, let's think about this intuitively. Suppose that in fact, we can think about this like a two-digit combination. So, let's say we're allowed to pick the digits 0 through 9 for both of those choices. For the first, we have a total of 10 different digits. Be aware that the size of this set is 10, not 9. Be careful. Now, for each of those 10 digits that we choose first, we have another 10 choices for that second digit. So, if we were to write down these 10 digits, off of each one of these, we would have 10 lines. And we would have 10 lines for each of those 10 digits that we have written down. And these lines would lead to whatever your second choice was. So the total number of things that you end up with at the end in this kind of tree diagram is 10 times 10, which is 100. So there are 100 possible combinations there. So that's the basic premise of the multiplication rule. But here, it essentially involves a more formal statement as follows. Let A be a set and let B be a set. Then the size of their Cartesian product is equal to the product of their individual sizes, just like that. So let's launch into the proof. For the sake of ease, we're going to say that the size of A is m and the size of B is n. That'll make it easier. Now, what we can notice is that sets of this form a partition over this set. What does that mean? Well, this A is an element of A. And so that keeps running through. So what this essentially is, this kind of set, is just the set of A, B, such that B is in B. That's all that is. For example, if we had some different A1, A2 in A, this A1 times B is the set and this one now if you have familiarity with how the Cartesian product works, you'll see that these two sets are disjoint. None of the tuples have the same first element, and hence they cannot be the same tuple. If you iterate that over every single one of the A's in A, you get a partition. Nice and simple like that. I would advise that you take some time to think about this step. It's the trick of the proof. Now, since we know that these are disjoint, we're able to take the union of sets of this form and have their size taken. Remember that by the sum rule, if we have the union of multiple sets which form a partition, then that is just the sum of the sizes of those individual sets. Observe, however, that if we fix the first element of these tuples, then the only thing that's allowed to change is this B. So, if B has our n elements, then the elements of this Cartesian product will simply be AB1, AB2, AB3, all the way up to our ABN, where BI is in B. Clearly, there should be n of these. So we're essentially looking at this. Now remember that if A is in A, well, there are m possible ways for that to happen, because there are m elements in A. So for each one of those m elements, we are adding another n. We have n plus n, etc. This happens m times. That is just n times n, which is the size of A, times the size of B, as required. So that's our proof of the multiplication rule. So, for the sake of completeness, I think it is wise to go through an example. This proof was a bit long, and it may not have given you the intuition for being able to use the multiplication rule to actually find the sizes of sets. So, let's do the following example. We'll make it another political one. Suppose we have to pick a governor and a constable for our locale. There are 15 governor applicants and 12 constable applicants. How many combinations of governor and constable can we have? This question is a classic example of the multiplication rule. So, how are we going to approach this? Well, I would define G as the set of governor applicants. And we know then that the size of G must be 15. Similarly, let this be the set of constable applicants, then we know that C is 12. From there, it's very simple to see that we can take G times C, because we're looking at those order pairs where the first element of that coordinate is the governor, and the second is a constable. Now, we can see that by the multiplication rule, we simply have the following. There should be 180 different combinations of governor and constable, or 180 different pairs that are possible. And that is the sum and multiplication rules. So, I apologize if this video was a little bit less polished than I might have liked to make. Obviously, this is my first video, so I'm not totally up to standard, as you might expect. I hope this explanation was fairly clear. If you have questions, leave them in the comments. I'm happy to answer them. And I will see you all next time for an exploration of the factorial.